Okay, guys, let's go ahead and start on the next section, implicit differentiation, which, if I'm not mistaken, is 3.5 in your book. Implicit differentiation is so named because you're dealing with an equation that where the relationship between x and y is implicit rather than explicit. And let me explain what I mean by that. Okay. If we have an explicit equation, that's where you can actually isolate y. So y is equal to, x sine x or something like that. You know exactly what y's relationship is to x. And so when you differentiate, you simply have to use the product rule here, and you have x cosine x plus the derivative of x times sine x, okay? And that's easy enough, okay? Now what you really need to understand, however, is the fact that, and we haven't really focused on this, but it should make sense to us, differentiating is actually an operation that you're doing to both sides of the equation, okay? So basically, just like you can add the same thing to both sides, and you can subtract the same thing from both sides, and you can multiply both sides of an equation by the same number, and you can divide both sides of an equation by the same number. So you can actually keep the relationship between the two sides of the equation by differentiating, okay? Well, that should kind of make sense to us. It's an operation. It's something that you're doing to the equation, right? Well, what happens... one too many humps on the M, but you get it. That's implicit, okay? What happens when I have y is equal to x sine xy? Y now has a relationship to x, but that relationship is no longer explicit. It is now implicit. Now, you can still take the derivative, but it takes, of course, a new sort of way of thinking in terms of derivatives. So let's actually start with something a little more mundane, a little closer to home. Let's say that we have x squared plus y squared is equal to 9. Now, most of us should recognize that that is the equation of a circle. And circle, of course, is not a function, and we've talked about that before, and the fact that you cannot solve explicitly for y without actually requiring two different functions, right? The positive radical would be the top half of the circle, and the negative radical would be the bottom half of the circle. And then you would have to take the derivative of both of them independently. Okay, well, that sounds like a huge pain in the rear end. But remember, I said that taking the derivative was an operation. It is actually something that you are doing to both sides. So if I take the derivative with respect to x of both sides, I remember my rules of differentiation, and that allows me to actually do this one on this side, term by term. Okay, well, I won't keep you in suspense. The derivative with respect to any variable of 9 is 0. It's a constant, right? Now, the derivative with respect to x of x squared is obviously 2x. The question remains, what is the derivative with respect to x of y? And here is why we do it after the chain rule, okay? It is basically a corollary of the chain rule, because you need to take into account the fact that y has an implied relationship to x. And therefore, that implied relationship winds up being the inside of the chain rule. Let me go ahead and explain it to you like this. Let's say I have y is equal to f of x, just as sort of like, y in terms of x in general, okay? Well, if I go ahead and I square both sides, and then I take the derivative with respect to x of both sides. Okay, well, here's the thing. That looks a little bit difficult. That should not, however. That should just be 2 f of x times f prime, or what we'll call df dx, right? So really, the derivative of y squared with respect to x is 2y dy dx. Okay, so we have 2y dy dx is equal to 0. Now, if you didn't quite get that on the first run through, then that's fine. That's why I'm going to go through gobs and gobs and gobs of examples. But this is sort of the justification for why we do it here. The fact that I have to, because this variable does not match with that one, I have to do it by the chain rule, because this variable, not being in terms of x, has an implied relationship to x, which is this variable's which is this expression's inside vis-a-vis the chain rule. And therefore, when I go ahead and differentiate it down to here, it shouldn't really be all that big of a surprise that I'm going to isolate the dy dx. That means pushing the 2x over to the other side, which makes it negative, and dividing by 2y, and I get negative x over y, and that is indeed the derivative of that circle at any xy coordinate pair. Okay? Now notice that your dy dx is not in terms of x, it's in terms of x and y. Because at any x, because it's not a function, just think about the shape of a circle, at any x you don't have an implied y, you have two implied y's. And therefore, in order to get the slope at that particular point, you actually need to specify which of the ordered pairs at any particular x value you're talking about. Are you talking about, are you talking about 0, 3 or 0, negative 3? Or just as an example, okay? So, now that you understand, or at least I've explained to you, whether you understand or not is a different issue. Now that I've explained it to you, let me go ahead and just distill the rule, okay? When you're dealing with implicit differentiation, it winds up being really, really easy. If I am looking for the derivative, okay, of some expression in terms of x, and that expression, if I'm looking for the derivative with respect to x, and it's some function of x, like, sine x, that becomes cosine x, right? But if the variable does not agree, meaning this expression is in terms of y, but I'm taking the derivative with respect to x, okay? I can still do this, but I have to take into account y's relationship to x, which is not explicit anymore, it is implicit. And therefore the sine, okay, so basically this is the derivative of sine stuff. Well, the derivative of sine stuff is cosine stuff, cosine y, times the derivative of stuff. Well, I don't know that relationship, so I'm going to shorthand the derivative of stuff just by saying dy dx, okay, or y prime if you want, okay? That is basically the long and short of implicit differentiation. If the variables agree, take the derivative as normal. If they don't agree, you have to tack on this derivative right here, which is basically sort of, like I said, the corollary of the chain rule. Okay, well, let's go ahead and do another example. We have x squared y plus y squared x is equal to negative 2. Now, this is a little bit more difficult than the original, because not only do I have implicit differentiation, I have the product rule in the midst of it. Now, I could change this into xy, x plus y is equal to negative 2, but that's not exactly a step forward, right? I still have to do the product rule, but in this case I have to do the product rule with 3 factors rather than doing it twice, one for each term, with 2 factors in each term. I'd rather just do it twice right here, okay, and sort of leave the 3 factor alone. That's like I said, not a step forward, more of a step backward. So let's go ahead and do it for the first term, and I'll put it in braces so we can see it a little bit easier. So the derivative of x squared with respect to x is going to be 2x, and I'm going to leave the second factor alone. Then I'm going to leave the first factor alone and then take the derivative of y with respect to x. And we'll shorthand it here as y prime instead of dy dx, but they mean the same thing. And then we'll do it for the second term. I'm going to go ahead, and if I take the derivative of y squared, well, y squared was in the last one. It wound up being 2y dy dx, and like I said, I'm shorthanding it as y prime. And then, of course, if I take the derivative of the first factor, I need to leave the second factor alone, and then leave the first factor alone and take the derivative of the second factor. Now, this is the hardest part, oddly enough, for implicit differentiation, is that people are so consumed with getting the variables all correct that you'll tell me that all of this is equal to -2, and it's not. Okay, the derivative, I don't care what variable you're dealing with, the derivative of a constant is always a constant. Okay, so beware of that. Now, here, the brackets and the braces really aren't doing anything, right? All they were doing was helping us see what we've done, okay? And it's, you know, it's kind of nice to be able to see what you've done, but now let's go ahead and rewrite it without all of that. Okay, now if I want to solve for y prime, it's just algebra from here, right? I just want to leave these two terms on this side. I need to take these two non-y prime terms and I need to shove them over on this side. Okay, so I'm going to wind up getting x squared y prime plus 2xy y prime is equal to negative, and I'll just go ahead and deal with it as a single negative entity. Okay, and then I need to factor out the y prime. Okay. Then, of course, I need to divide through in order to isolate. Sorry, kind of got ahead of myself there. I need to divide through in order to isolate the y prime, and therefore the y prime, as we see, is negative y squared plus 2xy over x squared plus 2xy. And if you see in there, there's sort of a symmetry in the way that the numerator and denominator is constructed, because there was a symmetry in the way that these terms were lined up in the original. But that will give you the derivative of the original equation for any xy coordinate pair. Okay? And that is how you take the derivative of that original implicitly. Okay. Now I could go ahead and go through how I simplified it into 3 factors. I think you can go ahead and do that on your own. I think we'd be better served by moving on to another example. So if we have 4 cosine x sine y is equal to 1. Okay. Well, you could divide both sides by 4 and get rid of that 4 and push it on over to the other side. But just in case you don't remember to do that, let's go ahead and just let's just join it up with the cosine x when we're doing the product rule. Okay, and we'll see the fact that it's going to disappear anyway. So we have the first times the derivative of the second factor. Now the derivative of the second factor, and I've already done sine y, if you remember, it's cosine y times y prime. And then I need to go ahead and do the derivative of the first, which winds up being negative 4 sine x, and then I need to go ahead and leave the second one alone. Now remember, like I said, and I try to give you a heads up and let you know where your mistakes are going to come from. The mistake is going to be you're going to put a 1 right here. And that is wrong, 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 wrong. Okay? You cannot put a 1 right here. It's a 0. Okay? So I have 4 cosine x cosine y, y prime, minus 4 sine x sine y is equal to 0. Okay. Now, we can go ahead and shove the sine one over to the other side. 4 sine x sine y. And I see the fact that the 4's are going to cancel out when I actually divide through, right? Because this right here is what needs to be divided through in order to isolate the y prime. And y prime, the 4's are going to cancel out, and when I divide sine x by cosine x, I'm going to get tangent x. And when I divide sine y by cosine y, I'm going to get tangent y. And that right there is my derivative that I've arrived at implicitly. Okay? Now, I mean, I guess you could, isolate the y on this one. Sine y is equal to 1/4 secant x, and then y is equal to arc sine of, secant x over 4 or something like that. But since you don't know how to take the derivative of inverse trig, which, by the way, that's coming down the pike, you really can't do anything with that. Okay, so your only recourse on the one that you've been given is to go ahead and do it implicitly, and it really wasn't all that bad. I mean, this is another one of those examples of a problem that's really not all that difficult. It's just burdensome in terms of the number of things that you're asked to take into account and asked to keep track of. So, not that big of a deal. Let's go ahead and do one more example, and then we'll be done with this particular video. So let's say we have y is equal to sine xy. And if we do this enough, you're eventually going to wind up knowing the derivative of x times y sort of by heart. So if we go ahead, and in this case I'm going to go ahead and remind you just by the notation that we are differentiating both sides, and that is an operation that I'm doing to both sides. So it's something that I'm doing to both sides. I'm doing in accord with the cardinal rule of equations, which is what I do to one side, I have to do to another. And this gives me dy dx is equal to, well, I know that this is sine of stuff. So what's the derivative of sine stuff? Well, the derivative of sine stuff is cosine stuff. Now, I need to deal with the derivative of the stuff, which is x times y. And that's x times the derivative of y plus the derivative of x times y. Okay, now you have two dy dx's. You need to go ahead and distribute this cosine across that binomial in order to free up that second dy dx from those braces that I put them in. Okay, and you get y cosine xy. And now I need to isolate. So basically the easiest thing to do is just to subtract this over to the other side and factor it out. So once I've pulled it over to the other side and factored it out, I'm going to have that. Okay? And then in order to solve for dy dx, it's simple division at this point. xy, 1 minus x cosine xy. And that is the derivative of the original arrived at implicitly. Okay. Now, in the next video, we're going to get not only to some more examples, but to a few tangent line problems as well. Because there are tangent lines to, implicitly defined curves, just like there are explicitly defined curves. So that ought to be a whole lot of fun. I hope that this has been helpful. I'll try to sort of backtrack and try to sort of explain it a couple more times as we move through these examples. But yeah, that'll do for this one, and we'll just go ahead and move on to video number 2.